then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing. Greetings, calculus students. This is not lesson 14, by the way. Today what we're going to do is we're going to review some of the tougher problems that were on the last two assignments. Today we're actually going to do, for our assignment, we're going to do a review assignment in AP Classroom. So believe it or not, we're actually not covering anything new today, but there were a few problems in our previous two assignments that I really need to address. So I'm going to take this time to address those particular problems. So let's go ahead and have a look. Okay, so the first assignment I'm looking at is the assignment from Monday. This is limits 12. And so this is, I just took one of the assignments from one of you guys. The person's assignment I took actually made 100 on this assignment. So that's outstanding. So as I'm looking at some of these problems, maybe numbers and stuff may be different, but the essence of the problem is the same. And I'm looking at number 8 here because we are still, believe it or not, having issues with this concept of what it means when a limit exists, or what it means when the value of the function at the point is defined. And so we want to clear that up once more. We initially had problems with this on an AP Classroom assignment, and we're still having a residue of issues with it. So we want to kind of clean all that up. So let me read what number 8 says. So number 8 says, if the limit as x goes to 6 of f of x is 10, which of the following must be true? Roman numeral 1, f of 6 should equal 10. So if the limit exists and it is 10, does that mean that the value at the point has to be 10? Does that have to be true? If I can show you one counterexample, that means it does not have to be true. And I can easily show you a counterexample of a limit existing and the function at the point not equaling that limit. So let me just go down to one of the graphs, another of the graphs in this assignment. Here we go. Let's look at where x is 2 right here. Here the limit as x goes to 2 is 1. That is not equal to f of 2. F of 2 is 3. And you guys have seen this type of deal a million times. So you have to internalize this information conceptually. You've seen this a million times. So this is a direct indication that the limit as x goes to c and the value of f of c do not have to be equal. In fact, if you look at where x is -1 right here, the limit could exist and f of c could not even be defined. Again, things you've seen before. So as I go back to number 8, okay, slow down, guy. As I go back to number 8, so the fact that f of 6 is 10 is not something that has to be true. And then these last two questions are questions about continuity. Does it have to be continuous, or does it have to not be continuous? And so let's go back to the graph we were just looking at. So here the limit exists. Obviously, that's not continuous. You have a removable discontinuity there. So just because a limit exists does not guarantee continuity. Again, here the limit exists. It does not guarantee continuity. So does that mean that if the limit exists, it's not going to be continuous? No, it doesn't mean that either. Here, for example, the limit at 3 exists. It's continuous. At whatever this is, 2.5, 2.6, the limit exists. It's continuous. Over here at 0, the limit exists. It's continuous. Over here at -2, the limit exists. It's continuous. I can think of an infinite number of points where the limit exists and it's continuous, but it doesn't have to be continuous, as you can clearly see from when x is 2 and when x is -1. So in short, what does a limit tell us when a limit exists by itself? All it tells us is that the limit exists. A limit exists does not tell me anything about continuity or the value of the function at the point. A limit could exist and you could be continuous at that value. A limit could exist and you could not be continuous at that value. A limit could exist and f of c could be defined. A limit could exist and f of c could be undefined. And a limit could exist, f of c could be defined and it can be a value different from the limit. And a limit could exist and f of c can be defined and it can be the value the same as the limit. So all of those things can go on. So the limit existing in itself, ipso facto, doesn't guarantee anything about the value at the point or about continuity and the lack thereof. All right. So hopefully we have finally put this issue to bed. Now let's see what else was interesting on this particular assignment. So this problem, albeit, I did problems similar to this in the lesson leading up to this, we still want to look at this problem nonetheless because people still have problems. And I'm sorry, I didn't specifically, even though I was saying that, I didn't specifically declare, the answer of this guy. And so obviously we show that none of these issues are true. So this answer was none of the above. Okay, so let's go back to this guy. And so let's look at how this guy works out. All right, so this is a problem. So I'm gonna go into my procedure for finding limits analytically. So I plug in 0 for x, and this will be the square root of 2 minus the square root of 2, which is 0 over 0. So that's a problem. And so I have the square root deal. When I have this square root deal, I think about rationalizing, and I think about rationalizing it when I have a sum or a difference with the same thing but the opposite sign. So this has a minus sign, so I'm going to write the same thing but with a plus sign and multiply it by the top and bottom. So therefore, I'm going to multiply the top and bottom of this function by the square root of x plus 2 plus the square root of 2. And again, that's top and bottom. All right, so what it does on the top is it gives me that a squared minus b squared deal. So that would be x plus 2 minus 2. It's going to be x, but I'll write x plus 2 minus 2 for right now. X plus 2 minus 2. The bottom, there's no need to distribute, of course, because again, what we're trying to do, our main objective here is to cancel out this x because this x is what's causing the problems. Again, the 0 in the denominator is the issue. So I really want to get rid of this x. So why would I want to distribute it if I'm trying to get rid of it? So x times the square root of x plus 2 plus the square root of 2. Okay, so 2 and 2 are going to cancel. X and x are going to cancel. There's going to be a 1 up there. You can now take the limit as x goes to 0. So that's plugging in 0 for x. So that'll be the square root of 2, and that's the square root of 2. So the square root of 2 plus the square root of 2 is 2 times the square root of 2, just like x plus x is 2x. So there is our answer. Okay, so you can see the answer clearly there. Let's see. So again, here's another problem going into how number 8 was. And in this problem, it's saying if f of negative 8 is negative 3, which of the following must be true. So now it's telling you the value of the function at the point is defined. And the question is, which of the following must be true? Does that mean that the limit has to be the same number? Or does it mean that the limit doesn't exist? Does it mean that it has to be continuous? Or does it mean that it has to be not continuous? And again, we can look at, I can just choose another graph from this same assignment and analyze this stuff if it's unclear. So first, let me investigate the value of the process of the function at the point in relationships to the limit either being the same thing or the limit not existing. Let's see if that is something that must be true. So I'll look at this graph here. Okay, so if I look at this graph, for instance, if I look at -1 when x is -1. Okay, so f of -1 is defined. And yes, the limit does exist. Okay, that's a possibility. But let's look here at x equals 2. Here, f of 2 is also defined. F of 2 is 2, but the limit does not exist. So just this one graph in itself tells you the function can be defined, the limit could exist, the limit could not exist. So neither one of those has to be true. So I couldn't select either of those limit options because it could be true, could not be true. So this is talking about which of the following must be true. So neither 1 nor 4 must be true. And 2 and 3 are talking about being continuous or not continuous. So if I know the value of the function at the point, does the function have to be continuous, or does the function have to not be continuous? Again, let's take a look. So here I know the value of the function at the point. It's not continuous. That's at x equals -1. At x equals 2, I know the value of the function at the point. The function is not continuous. So you might be thinking, well, that means if I know the value of the function at the point, it means it's not continuous. No, absolutely not. There's an infinite number of numbers I can check where it is continuous. So all of these numbers here, pretty much all the numbers from -3 to 4, except for at -1 and 2. And there's an infinite number of numbers between -3 and 4. So I'm not just talking about integers. I'm talking about all these numbers here. Negative 2.917, -2.9178, etc. There's an infinite number of numbers just right here. And so there's an infinite number of examples where I know the value of the function at the point and it is continuous. And there's also a couple of examples where I know the value of the function at the point and it is not continuous. So none of those must be true. None of those have to be true. So just like number 8, the answer to this one is none of the above. Okay, well, let me see, was there anything else on this assignment? This was our squeeze theorem problem here. And it's showing you that this function g is squeezed between f and h. And so this is g, a very crazy looking function that otherwise you probably wouldn't know how to find its limit. And we're trying to find the limit as x goes to 0. So again, since it's squeezed between these two, if I find their limit as x goes to 0, then if they're the same, then I'll know the limit of the middle function as x goes to 0. And these are pretty easy functions and they're polynomials. So the limit of x squared as x goes to 0 is 0. I'm just doing direct substitution. And for negative x squared, that's also 0. So the limit of the two outside guys are 0. So the inside guy must be 0. Okay, so the value of the inside guy must be 0. Now, just something to understand, and this is going to be important on some of the problems you're going to see today. And I probably didn't write these answer choices in the best light. When you have a limit that you have to use the squeeze theorem for, meaning there's no other way you can find a limit, at least of the methods that you know of right now. And let's say hypothetically, these two outside limits are not the same, then that's something that cannot be determined by the information you have. So really, this should have said cannot be determined versus does not exist based on the information you know. So if you're doing a squeeze theorem problem, and this is going to happen on today's AP Classroom assignment, and the two outside limits are not the same, then you're unable to determine the limit of the inside function. Unless, of course, it's a function where you know how to find a limit, but typically it's not going to be that type of function. Okay, let me see if there was anything else on Monday's assignment. Everything else is looking pretty vanilla. Yeah, that was nothing. So let's go to yesterday's assignment. This is assignment from Tuesday. This is functions 13. I did announce there were some mistakes on this particular assignment. So, and what I decided about this, and a couple of people have asked me about redoing the assignment. What I'm going to do on this assignment, because of the mistakes, and it would take too much time just to look at each particular person's paper and see exactly who these mistakes affected and who they didn't. I'm just going to give you guys a completion grade on this assignment. This is limits 13 I'm referring to, but I do want to still address and look at some of the harder problems on this particular assignment. So I don't remember the numbers. Again, this is some students' paper that I'm looking at. And yeah, this is one I want to look at. So I want to begin at looking at this number 2 here. And the thing you guys have to realize when doing problems, you have to realize it has to be over information that I know, and think of the things that you know that apply to that particular situation. So here it says, let f be a function which is continuous on the closed interval from 1 to 3. There's really only one thing we talked about that referred to functions which are continuous on a closed interval, and that is the intermediate value theorem. So that statement there shouldn't have you thinking, oh, maybe intermediate value theorem. And it says that f of 1 is 10 and f of 3 is 18. Which of the following statements must be true? And letter A says that f of 2 has to be between 10 and 18. Now, do you think that has to be true? Let's think about it. So let me draw a graph real quick. So my points are 1 and 10 and 3 and 18. 1 and 10. So let's say this is the point 110. And let's say this is the point 318. So the problem is saying that f of 2 must be between, let me get back to exactly what it's saying. Yeah, f of 2 must be between 10 and 18. So greater than 10, less than 18. And it might sound like that should be true, but it should not. So let's say for the sake of argument, this red line is where x equals 2. Now I got a continuous function. Now if I have a continuous function, does f of 2 have to be between 10 and 18? No. It could be down here. It could be less than 10. That's not between 10 and 18. If that's the graph of the function, or it could take this route. F of 2 could be greater than 18. So f of 2 does not have to be between 10 and 18. That's not true, and that's not what the intermediate value theorem tells you. Again, what IVT tells you is there is at least one number where f of that number, where that number between these two numbers, where f of that number is a number between 10 and 18. It doesn't tell you what that exact number is. So anytime it talks about an exact number, that can't be justified with the intermediate value theorem. Just tell you one such number exists. So there's no information in this problem where we know exactly what the value of f of 2 is. Now, if I'll say this, if it said the function is increasing, then f of 2 would have to be between those two, because meaning the function is increasing on this interval, meaning for the whole interval it increases. Then it would have to be between the two, because this example I got here, the function increases then decreases. On this example, decreases then increases. But just because the values increase doesn't mean the function is increasing on that interval. That's very important to remember, particularly when we do some stuff a little bit later. If you see sometime they give you a table of values which are increasing, that is not enough evidence to tell you that a function is increasing. So in situations like that, they have to make a statement that the function is increasing. If that statement is not made, you can never assume that a function is increasing, particularly when you just see table of values. So letter A isn't true. Letter B, we haven't talked about derivatives yet, so anything that's referring to derivative is not going to be true. Letter C, I actually just spoke on that. We can't assume just because f of 3 is greater than f of 1 that the function is increasing on the complete interval. So the answer that's true is answer D, because it's saying that f equals 17, and 17 is a number between 10 and 18, has at least one solution on the interval. And that's what the intermediate value theorem states. It can't tell you the exact value. Again, it's an existence theorem, so it can't tell you the exact value of the number. It's just saying some number exists where f of that number is going to give you a value between 10 and 18. So that answer would be D. And also number 3, so this was a pretty good problem. And there's different ways of doing it, and you may have a way easier than mine. The actual answer you see here, the person that did this selected the right answer that was in the system, but that's actually the incorrect answer. The actual right answer is negative square root of 2. So this is the actual correct answer. And let's look at one way of finding this particular limit. Okay, so I ran out of a little space writing the problem, but you can see I'm finding a limit as x goes to pi over 4. How I like to do a problem like this is just some principles dealing with manipulating trigonometric functions. Something that got taken away from us a little bit in pre-cal last year because the year kind of got closed down early, right when we were about to get into stuff like this. But just to kind of give you a brief introduction to manipulating trigonometric functions like this, one thing that we like to do is we like to write things in terms of sine and cosine. So what I'm going to do is I'm going to play with my numerator a little bit, and I'm going to turn tan x into sine x over cosine x. Because most people understand that's what tan x is. That's called a quotient identity. And then I want to make this one fraction, so I need a common denominator. That common denominator will be cosine, so I'm going to turn 1 into cosine x divided by cosine x, of course, minus sine x divided by cosine x, which will give me cosine x minus sine x. They have a common denominator all over cosine x. Now this is the numerator, right? This is just another way of writing 1 minus tan x. And that is over sine minus cosine. That's the denominator. That's over. I'm not going to write it. I'm going to show you why in a second. So this is supposed to be over sine minus cosine. Well, actually, maybe it may be beneficial to write that. So this next part, people are with me. So that's over sine x minus cosine x. Okay, so basically this is being divided. This fraction is being divided by sine x minus cosine x. Well, what do we do when we divide with fractions? We multiply by the reciprocal. So this is actually cosine x minus sine x over cosine x times 1 over sine x minus cosine x. And we talked about this situation before, when you basically have the same two terms, but they're different signs. Here's a negative sign, there's a positive sign, there's a negative cosine, there's a positive cosine. So they simplify and give you -1. So this becomes -1 over cosine. And I'm trying to take the limit as x goes to pi over 4. Cosine of pi over 4 is the square root of 2 over 2. So that's -1 over the square root of 2 over 2, which again, when you divide, you multiply by the reciprocal. So that's -2 over the square root of 2. And another way of writing that, if you multiply the top and bottom by the square root of 2, would be -2 times the square root of 2 over 2, which is just the negative square root of 2. So that's how that problem went. That guy was a doozy. Let's see what else was interesting on this assignment. Okay, light work. This is pretty light, but I just want to comment on this problem. Whenever you see a horizontal asymptotes come from limits as x goes to infinity. They come from limits at infinity. So whatever statement must be true, and we're talking about a horizontal asymptote, it must be a limit where x is going to infinity. So that's why this is C. Now, if it's a vertical asymptote, it's a limit that equals infinity, like it's an infinite limit. So if this said vertical asymptote, it would have to be D, either the left-handed limit or the right-handed limit, or the whole limit itself is going to either infinity or negative infinity. So horizontal asymptotes, we're talking about limits at infinity. Vertical asymptotes, we're talking about infinite limits. Okay, that shouldn't have been a problem. That shouldn't have been the problem. This problem on this person's paper number 8. So this is the problem that I disclosed in the email. There was a mistake. This number was supposed to be positive 18. It was supposed to be x minus 9 times x minus 2 for this particular problem. The x minus 2s would cancel, meaning you wouldn't have any infinite discontinuities because you wouldn't have anything left in your denominator. Since I wrote the problem wrong, technically nothing would cancel because this can't even be factors. So, technically the way the problem is written, you would have got x equals 2 as your vertical asymptote. So again, I'm giving you guys completion grades for this assignment because of mistakes like that. Okay, let's see. So another one of these are becoming interesting problems for us. So this says, if f has a removable discontinuity, which of the following could be true? Now, I didn't say which of the following must be true, but which of the following could be true. And so let's look at it. So I'm pretty sure later on this assignment, I got a graph that I can refer to. So the things we're checking, if it has a removable discontinuity, f of c is not defined. Could that be true? The limit not exist. Could that be true? The limit exists. Could that be true? Or the limit not equaling f of c. So let's explore all of those things. Let's see, is this a good example to use? Well, I'm looking at it, so I'll go ahead and use this example. So here I have a removable discontinuity at x equals -5. I have a removable discontinuity at x equals -5. So my limit exists, correct? In fact, I'll look at 2 removables on this graph. I also have a removable discontinuity at x equals 4. Also, the limit exists. Now, remember, when you have a removable discontinuity, basically the whole graph is intact, but you just have a little open circle there. And maybe the open circle is defined somewhere else on that value, or maybe the open circle, where the open circle is, the value is not even defined. But since the rest of the function is the same, the limit is always going to exist on a function on a point where you have a removable discontinuity. The limit will always exist. So it could not exist. That's something that could not be true, that the limit does not exist. The limit exists at removable discontinuities. Now the other issue, so the limit does not exist 2, that can't happen. Definitely the limit could exist 3, that definitely could happen. So the other 2 things to consider, can f of c not be defined? And could the limit not be equal to f of c? And we can see both those things in this particular graph. Here, where x equals 4, removable discontinuity, and f of 4 is not defined. So that definitely could happen. And here, where x equals -5, removable discontinuity, and f of -5 is defined, but the value of f of -5, which is 3, is not equal to the value of the limit as x goes to -5, which is 7. So both those items could be true. So in this particular problem, everything could be true except for the statement that the limit does not exist. So 1, 3, and 4 could all be true. Okay. So here we have a table. For there to be some c between 1 and 7, those are the range of the x values, such that f of c equals 10. 10 is a number, if you look between the 2 endpoints, which of the following conditions must be true? So when I talked about the initial value theorem, IVT, and I talked about the importance of understanding the conditions on the theorems we're going to cover. And I said, really the main one when we're talking about EVT, extreme value theorem, IVT, and MVT, the mean value theorem, is whether they are continuous or differentiable. That is really the main one to look at. And again, earlier I said, we can't determine if a function is increasing or decreasing just based off a table of values unless they tell us that. So, which must be true for me to make this statement, that's IVT, which must be true is that the function is continuous. So that's the only thing I need to be true. Okay, let's see what else, if there was anything else on this particular assignment. So this is This one, 14, is the one dealing with the vertical asymptote. And again, for the vertical asymptote, you need the limit to equal infinity. So that would be C, of course, as this person selected. Again, horizontal asymptotes are limits where x goes to infinity. Vertical asymptotes are limits where the value is infinity or negative infinity. Okay, you guys are very good at these problems. That's something you should have known from memory. Okay, I do want to look at 18. Oh, that's the last one. So 18, even albeit I did a problem very similar to this in the lesson, I think in Monday's lesson, I'll still visit this problem nonetheless. All right, so when I do a problem such as this, what I like to do is get rid of these fractions by multiplying them by their least common multiple, the least common multiple of their denominators, which in this case will be 2 plus x times 2. I have to multiply the top and the bottom by that guy. And so when I do the top, the 2 plus x's are going to cancel. I'm going to be left with 2 minus, when I do the bottom, the 2's are going to cancel. I'm going to be left with 2 plus x. My denominator, I'll just leave it be x times 2 plus x times 2. And again, here, I always forget to do this little routine deal. If I plug in 0 for x, I'll be 1/2 minus 1/2, which is 0, which is, of course, over 0. The problem in the problem is this x in my denominator, because that's what's making my denominator 0. You can see up here, these 2's are going to cancel. Now, this minus sign is going to be distributed to this x. So that's going to be a negative x. So it's going to cancel with this. Well, I should write that because I don't want the negative sign to cause a problem for you guys. So this is a negative x up here times x, 2 plus x times 2. So that x would cancel. So that will be -1. So you have -1 over 2 plus x times 2. And if you take the limit as x goes to 0 of something like this, you can just plug in 0 for x. And that's -1 over 2 times 2, which is -1 over 4. All right, so that concludes our look at some of our harder problems on the previous 2 assignments. Again, today you're looking at some stuff in AP Classroom. You should be properly prepared.